All right, can everyone see the screen? Yes, all right, then we will begin the pop talks with Akash Gupta.
Hang on, it looks like the screen is black.
Yeah.
Can you try resharing or maybe not do full screen view?
Yeah, I might have to do that. Let's see. Okay, yeah, looks like I won't be able to do full screen. So let's just see if this works on its own. Is that better?
Yeah.
Okay, great. Sorry about that.
Okay, thanks, Chris. Hi, everyone. I'm Akash Gupta. I'm a PhD candidate at UCLA, where I work with Hilka Schlichting. And my poster here is about how we can understand the radius valley, which, as shown in this left-hand side plot, is this lack of planets around 1.5 to 2 Earth radii, where the smaller planets are like somewhat rocky and the larger planets probably have a lot of hydrogen helium envelope. And so basically how we can understand this observation under the core part mass loss mechanism, that is, as a byproduct of the planet formation process itself. If you'd like to know more about this process and what we have got to know through this work, please check out my poster or contact me through Slack or through other means, and I'll be really happy to answer, to talk more about this. But basically, the main takeaway of this work of this poster is that the core part mass loss mechanism can not just reproduce, explain, and predict the location or the shape of this radius valley or the relative occurrence of planets, but even the trends in the planet size distribution with all repeated insulation flux and stellar properties like mass, metallicity, and age. And that's it from me. Thank you so much.
Great, thanks. Next up is Mike Correclock McKeon, if he's here.
Hi, everyone. I'm Mike Correclock McKeon, and I'll have a poster up in the Slack soon about constraining and updating the masses and densities for the 3 Kepler-289 planets, which are orbiting the young sun-like star Kepler-289. The 3 planets are near a 124 Laplace orbital resonance, but not quite. We made a transit observation of the outer planet, Kepler-289c, with the 200-inch telescope at Palomar Observatory, right here in Southern California. And we extended the TTV baseline by more than 6 years from the original Kepler observations, as well as doing a reanalysis of the Kepler photometry to more carefully account for star spots. We were able to reduce the mass uncertainties by more than a factor of 2 and show that the system is consistent with 2 super-Earth planets with considerable atmospheres and an outer Jupiter-like planet. If you're interested in hearing more about it, check out the poster on Slack.
Great, thanks. Next we have Joshua Garrett.
Hi everyone, my name is Joshua Garrett. I'm a grad student over at CSUN. So for our research, we focus on the potential for planet formation in the protoplanet disks that are at the end of their disk lifetime. One of the obstacles of planet formation is the radial drift problem, in which grains that are about millimeter in size at cell-centric distance about 100 AU move inwards to the star in less than a year. So dust trapping is a potential solution to radial drift problem, in which grains actually concentrate in local Pressure maximum along the disk. So we focus on the spectral index of 24 protoplanetary disks that are in the upper scope. So this region is about 5 to 10 million years old. And then from the spectral index, we infer grain sizes, and we confirm whether or not dust trapping is a efficient mechanism throughout the disk lifetime. So we have values for the alpha for spectral index that go from 1.5 to 3.1, and we have a sort of an analysis in which we approach the results with a 2-disk model in which the emission is either awfully thin or awfully thick. And if you guys would like to hear more about it, we also include sort of a program called RADMC3D, which is a radial transfer code, and we explore disk models that have scattering by dust as well.
Great, thank you. Next, we have Samson Johnson.
Actually, it's Kaylin.
Oh, never mind, Kaylin.
Yeah, I'll get there. Hi, folks. I'm presenting this on behalf of the Microlensing Science Investigation Team for the Roman Space Telescope, which was recently renamed from WFIRST to honor the legacy and scientific contributions of Dr. Nancy Grace Roman. The Roman will use its wide field imager to conduct a 2 square degree multiband survey of the galactic center in the near infrared, spanning a total of 432 days over 6 observing seasons. The primary goal of this Roman Galactic Exoplanet Survey, or ARGUS, is to detect and characterize exoplanets, both bound and free-floating, using gravitational microlensing. Simulations indicate that the ARGUS will detect approximately 1,400 cold and bound exoplanets down to the mass of Mars, as well as over 150,000 transiting exoplanet candidates. I will specifically highlight the work of my collaborator, Samson Johnson, a graduate student at The Ohio State University, whose recent paper predicts the ARGUS will also detect roughly 250 free-floating planets with sensitivity down to the mass of Mars. And I'll note that he's on the job market as well. So thanks for listening, and please check out my poster in the Slack channel for more information.
Great, thanks, Caitlin. Next, we have Margarita Epstein-Martin.
Hi, I'll get the poster on the Slack soon, but so my work focuses on a triple star system where one star has a protoplanetary disk around it, and I've used a Lagrange-Laplace expansion to examine the dynamics at work, and turns out that even in the low inclination limit, the stellar spin axis can undergo some chaotic motion. So I've looked at the limits of chaos in that system. And if you'd like to talk to me more about it, hit me up on Slack.
Great, thanks, Marguerite. Next up is Sophia Cuevas. Sophia, are you?
Sorry.
No,
Yeah. So I've been working with Sarah Blunt and Jason Wang to model or find biases in orbit fitting, specifically in their Python package called advertise. And I've specifically been working on planet-on-planet interactions and seeing how those play into current orbit fitting and incorporating an n-body simulator into this, and working with finding the difference between their current Kepler solvers that exist and how n-body simulators can improve accuracy and precision.
Great, thank you, Sophia. Next, we have Yejuan Bi.
Hi, I'm Yejuan from Brown University. I'm currently studying physics and computer science, and I'm an applicant for this year's PhD application cycle. This summer, I worked at JPL on employing different unsupervised and semi-supervised learning techniques to predict exoplanet host stars from stellar elemental abundances. And we experimented with different types of methods that was different from existing methods in the literature, which was modeled around a supervised learning framework. We employed unsupervised learning techniques because it was more applicable to the structure of our data set, where we didn't have access to true negative data points, which is essential for a supervised learning framework. In the end, we were successful and able to define potential bounds for the different elemental features of the host stars, and thus we can use that information to predict future host stars from an unknown host stars set. Yeah.
Great, thank you. Next, we have Kim Bott.
Hi, I'm Kim Bott. I'm a postdoc at UC Riverside working with Stephen Kane. I just came down here from University of Washington in Seattle. My poster is on research mostly conducted there at UW on polarization for terrestrial exoplanets and mini Neptunes. This is utilizing a new, robust, polarized radiative transfer modeling software to provide more accurate predictions that we just won a ROSAS grant for to further develop. And I've run similar models for hot Jupiters, if those are more your things, and done observations of hot Jupiters. I'm very keen to talk about the science that we've already done with observations paired with models or these predictive models. I think I'm the third poster down in the Slack channel if you want to find me there.
Great, thank you. Next, we have Etienne Bachelet.
Yes, I'm postdoc at Las Cumbres Observatory, and today I'm going to present the new key project we have at LCO, which is a detection of planets across the entire Milky Way. So I plot on the first figure the current known planets, and we can see that there is some bias. Like, for example, John Zink says this morning, the planet occurrence is dependent on the metallicity, and 95% of the planet we know are located very close to the Earth. So that can indicate that our current sampling is biased. But fortunately now we have new all-sky surveys that allow to detect microlensing events across the entire Milky Way. So the Omega strategy is based on collecting microlensing candidates from this all-sky survey, such as ETF and Gaia, and use the LCO telescope network to make intensive follow-up. And using this strategy, we found the first microlensing planet in direction of the anticenter of the Milky Way. And since July, when the project started, we already catch 4 planets. So you can come to the poster to talk more about this.
Great, thank you. Next, we have Isabella Angelo.
Hi, my name is Isabella Angelo. I'm a second-year graduate student at UCLA, where I work with Eric Pettigara and Smadar Naus. And our project is investigating the extreme eccentricity of a sub-Saturn called Kepler 1656b. So we spent some time scratching our heads trying to find a source of the eccentricity, and then recently we noticed a potential signal of a second planet in our radial velocity observations. So we're currently working to collect more data that can discriminate between 1 and 2 planet models. And that will tell us how likely it is that a second planet can be inducing the eccentricity via the eccentric Kozai-Lidov effect. So if you're interested in sub-Saturns or dynamics, eccentric systems, or planet formation, feel free to message me or check out our poster on the Slack.